Dear students, this is our 13th lecture on organic reaction mechanism, and we are continuing uh, our discussion on reactive intermediates, and today we will be discussing nitrenes. Nitrenes, as you know, they are neutral, electron deficient molecular species that contain a monovalent nitrogen species containing 6 valence electrons. So 2 electrons they have been used in forming a covalent bond with other entity, and there are 2 lone pair of electrons present on this nitrogen, and such type of reaction intermediates which are formed during the reaction, they are known as nitrenes, and they are analogs of carbenes, which we have already discussed, and most of the reactions and their mode of generation, they are almost similar to carbenes. And as far as stability of carbons, nitrenes is concerned, here if you see that in comparison to carbon, nitrogen is more electronegative. So when electron activity of nitrogen is more, that means it will hold this pair of electrons more closely towards its nucleus, and this will decrease energy. And whenever we know that if energy of the system is decreased, then stability will increase. So, in comparison to those intermediates where there is no electron activity difference, the stability is more because of the electron active nature of this nitrogen atom. And like carbenes, nitrenes, they are also of two types: singlet nitrenes and triplet nitrenes. And again, in the same way, if they are spin paired, then we will call those as singlet nitrenes, and if they have unpaired electrons, then we will call them as triplet nitrenes. And both of these, they have sp hybridization in case of singlet as well as triplet nitrenes. The most common one, that is unsubstituted nitrane, is amidozine, where nitrogen group is attached to a hydrogen. So this is the simplest nitrane, and because of only these two groups, nitrogen and hydrogen, this is a highly symmetric molecule, and hybridization is sp hybridization. So as we know that there are 4 non-bonding electrons that are present on the nitrogen atom, and these 4 non-bonded electrons, they are distributed in a sp orbital. Two A pair of uh, electrons is present in sp orbital, and 2 electrons they are present in 2 degenerate either px or py orbitals. So because of this, there is a possibility of several type of electronic configuration which can be there for this type of combination for 4 non-bonded electrons. But the lowest electronic states in case of amidozine, they are triplet and singlet states, and singlet state being a doubly degenerate state formed by LCOM, linear combination of molecular orbitals, which are called as closed shell or open shell singlet configuration. So if we see the triplet amidozine, then we will have 2 electrons present in the sp hybridized orbitals, and 1 unpaired electron will be present each in px and py orbitals. And because of the presence of hydrogen, these px and py, they are not uh, uh, they are degenerate and they have the same energy, px and py, and that is why either one electron is present in px or other is present in py, and such type of presence of electrons gives us a triplet nitrene, whereas singlet nitrene can have these two types of doubly degenerate states, that two electrons they are present in sp hybridized orbital, and other two electrons in a paired form may be present in py or px, and because the energy is same, it hardly makes any difference that whether the two electrons they are present in px or py, so they will give same type of chemical and physical properties in case of singlet amidogen. Now if we replace the hydrogen by some other molecular group, then it will become Nr, and when we replace hydrogen by some molecular group, any alpha donor group, then the degeneracy of px and py orbital is removed. So the energy of px orbital increases in comparison to py. So the degeneracy which were present in unsubstituted nitrene has now been removed. So therefore the substituted nitrenes they have different energy as compared to unsubstituted nitrene. So here also you can see that here this is the triplet substituted nitrene. Again, two electrons they are present in sp hybridized orbital. One is present in py, other is present in px, and the spin is parallel in both the cases. They have same direction of the spin in case of py and px. And another type of singlet open shell state is that where the spin of these two electrons present in px and py orbital they are opposite to each other. So one has spin in the upward direction and other is having in the downward direction. So this is the difference between this triplet state and this open shell singlet state. So in actual their spin will cancel each other, so that is why this is a kind of triplet state only, because this will not show paramagnetism. Then the closed shell singlet state can be two electrons in sp hybridized orbital, and then the remaining two electrons may be present in py or may be present in px orbitals. But here we need to remember that the energy of py and px here is not the same. So there is a difference in energy of these two orbitals. Then triplet state is more stable than the singlet state, and if we compare the energy difference between amidogen, that is unsubstituted nitrene, then triplet is stable than the singlet by this much amount of energy. That is we require 36 kilocalories per mole of energy to convert a triplet nitrene, which is unsubstituted triplet nitrene, into unsubstituted singlet nitrene. So this is the amount of energy required for conversion of a more stable triplet state into less stable singlet state. Then generation of nitranes. Nitranes, as you know, they are very reactive and formed as reactive intermediates during a reaction, and therefore they have the tendency to get converted into stable product, and because they are so reactive that they are not generally isolated during the reaction. The most common method for the generation of nitranes is from azides or acyl azides. So when azides or acyl azides, they are heated or irradiated with UV light, so either thermally or photochemically, they are converted into nitrates with the elimination of one molecule of nitrogen gas. Similarly, this will give us alkyl nitranes, whereas this will give us acyl nitranes as the product. And this is similar, this method is similar to the method which we have seen in case of formation of carbenes from diazo compounds. So here, there we were using diazo compound, here we are using azides, and this is the most common method for the synthesis of nitranes. Then nitranes, they can be synthesized or generated through alpha elimination. Alpha elimination is when both the groups, they are eliminated from the same entity. So for example, if we are having these types of n substituted amines, so when H and this X is leaving group, they are removed from the nitrogen only. That type of elimination is called as alpha elimination, because both the groups, they are being removed from the same atom. So we will get alkyl nitrenes as the product from alpha elimination. Then third method is from sulfonyl amines, and here when phenyl isothiocyanate, these types of sulfonyl amines, they are heated in the gas phase, we will get phenyl nitrenes as the product with the elimination of one molecule of sulfur monoxide. Then fourth method is from iodinium amides, or these are also known as amino iodines. These are very important intermediates which are used for the synthesis of nitranes. So when these types of N-tosyl aminophenyl iodines, they are heated or they are radiated with UV light, that means either thermally or photochemically, they will remove this phenyl iodide from this, and we will get tosyl nitrines or nitrenes as the products. And these are very important iodide salts which are used for synthesis of many types of organic compounds. Then fifth type of reaction is from isocyanates. So when isocyanates, they are either heated or they are radiated with UV light, they are converted into alkyl nitranes with the elimination of one molecule of carbon monoxide. So one molecule of carbon monoxide is removed from here. We know that carbon monoxide have carbon oxygen triple bond. So two electrons from here, they will be shifted to the carbon monoxide, and if one molecule of carbon monoxide is formed, and alkyl nitrene is formed as the product. Not product, the intermediate. Then from N-benzene sulfonoxycarbamates, so these types of compounds, N-benzene, so this is benzene sulfonyl group, and this part is called as carbamate group. So N-benzene sulfonoxycarbamates, when they are reacted with a base, then base will first remove this proton present on the nitrogen, and then ultimately we will get these types of nitrenes as the product with the elimination of aryl sulfonyl aryl sulfonic acid as the product. Then reactions of nitranes, as we know that nitranes, they are reaction intermediates and they cannot be isolated and they are very reactive. So they have the tendency to undergo different types of reaction to give us the stable products. And most common among the reactions of nitranes, they are addition reactions. These are similar to what we have seen in case of carbenes. Similarly, insertion reactions, these are also similar to what we have seen in case of carbenes. Dimerization was also there in case of carbenes. So they have almost similar type of reactions which we have done in case of carbenes. Then another type of reactions of nitranes is hydrogen abstraction. Then metal nitrene complex reactions. This is again similar on similar lines which we have seen in case of carbenes. Metal carbene complex reaction, that is formation of carbenoids. So here also such type of reaction we will discuss. Then some rearrangement reactions which involve nitrenes as the intermediate, and among these, the most common is Hoffman, Curtius, Schmidt, and Lawson. So these are the four rearrangements which are having nitrenes as the intermediate in these reactions. Then first is addition reactions. Like carbenes, nitrenes, they also undergo addition to carbon-carbon double bond, and the reaction again is similar to carbenes, that addition of singlet nitrenes is stereospecific, whereas that of triplet nitrenes is stereoselective. Stereospecific means only one isomer is formed. Stereoselective means both the isomers they are formed, but one is formed in more amounts and other is formed in less amounts. Now we know that singlet nitrene is having two electrons present in sp orbital and two electrons present in the px or py orbital. Now, so because this pi bond of the double bond will also have two electrons with opposite spins, so these opposite spins they will interact with the opposite spin of the electrons present in the nitrane, and we will have a reaction intermediate stage like this. uh, a transition state is formed where this nitrogen is bound to both the carbons. One electron from here antiparallel, other electron from here antiparallel, they will form a bond and a transition state of this type will be formed. And this transition state will lead to the formation of a stereospecific product. That is, only one isomer is formed in such type of conversion. That is, singlet nitrenes, they will give us only one isomer. So that is why we call these reactions as stereospecific reaction in case of singlet nitrenes. Similarly, triplet nitranes, the mechanism is same as we have studied in case of carbenes. So here it is stereoselective. You know that the spin of both these unpaired electrons is a parallel spin. So in the first step, one electron will interact with the electron with opposite spin and they will form a carbon nitrogen bond like this. Then this remaining electron with this spin, and now we can see that spin of both these electrons is same direction. So that is why a bond formation cannot take place. So here first, in a slow step, spin inversion will take place. That is, uh, here this will get inverted. Spin will be in the downward direction. And now there is a possibility of formation of the carbon nitrogen double bond. and this will undergo cyclization to give us these types of aziridines as the product. So one isomer of aziridine is formed when this undergoes spin inversion and gives us the product. Then because this is a slow step, this in a very fast manner in the meantime can undergo rotation of the carbon-carbon bond. This carbon-carbon bond can undergo rotation. That means R will become beta and H will become alpha. So we will get through carbon-carbon bond rotation this type of transition state will be formed, and then this again will undergo through a slow step spin inversion, because these two still have the parallel spin, so they cannot combine to form a carbon nitrogen double bond. This will undergo spin inversion, and now this can cyclize to give us another isomer of aziridine. So we can see that now here in case of uh, triplet nitrenes we are getting isomeric mixture of products, and amount of each of the isomer formed will depend on that how much time this conversion takes place and how much time this conversion takes place. So depending upon the stability of the transition states in both the routes for the formation of products, the amount of each of the isomer will be determined. So that is why such type of reactions where we get isomeric mixture, they are called as stereoselective products. So in nutshell, singlet nitrenes, they gave us stereospecific products, whereas triplet nitrenes, they gave us stereoselective products. Then insertion reactions, these are again similar to what we have seen in case of carbenes, and nitranes. Out of nitranes, the most preferred ones which undergo insertion reactions, they are acyl nitranes or sulfonyl nitranes or ester group containing nitranes. So they generally undergo insertion reaction in carbon hydrogen bond. So for example, this is an ester containing azide. So this will give us an ester nitrene. So here nitrene formed from azide A insert into this compound. This is an optically active hydrocarbon S3-methyl hexane in presence of dichloromethane as solvent. Then this product is formed as the this carbamate is formed as the product, and we can see over here that the nitrene adds at this carbon hydrogen double bond. That insertion of the nitrene takes place around this carbon hydrogen bond to give us this product with retention of configuration. And if we see that whether the mode is a thermal mode for this reaction or a photochemical mode, the observed rotation in the formation of this product, because we have started with an optically active reactant and we have got an optically active product. The optical rotation which is observed, the observed rotation is independent of the concentration of the chiral alkene. So whether it is thermal or it is photochemical, so you can see that observed rotation is almost same whether the concentration was 100% or 1.2%, 26.8% or 100% photochemically. This 100% is in a thermal reaction, and in all the cases the retention of configuration is also about 100%. So the product is formed with retention of configuration. So higher the concentration of triplet nitrene does not affect the observed rotation. So that means the triplet species is unable to insert into these carbon hydrogen alkyl bonds. So this is only the singlet nitrene which adds to the alkyl carbon hydrogen bonds. Then, as I have told you that singlet nitrenes, they insert into alkyl carbon hydrogen bonds selectively and with retention of configuration, which we have seen in the last example. And triplet nitrenes, they do not insert into alkyl carbon hydrogen bond. So order of selectivity of the singlet nitrene toward insertion into alkyl carbon hydrogen bond is most preferably tertiary carbon hydrogen bond is inserted very easily in comparison to secondary or primary. So order of selectivity is that tertiary is more than secondary and secondary is more than primary. So you can see these two examples. So if we are having butane and we insert nitrene into it, of course singlet nitrene, because triplet nitrenes, they do not insert into alkyl carbon hydrogen bonds. So there are two types of carbon hydrogen bond. One is this one and other is at the carbon hydrogen at the terminal positions. So this is a secondary carbon hydrogen bond, whereas this bond will be a primary carbon hydrogen bond. So you can see over here the ratio of the product formed is 9 is to 1. That insertion at the secondary carbon hydrogen bond is 9 times more as compared to the insertion at primary position, that is here carbon hydrogen bond at this terminal carbon. Similarly, if we are having 2,3-dimethyl butane, we have substituted two hydrogens by methyl groups from this. Now this carbon hydrogen bond is a tertiary carbon hydrogen bond, whereas all these 4 methyl groups, they are having carbon hydrogen bond which are primary in nature. So you can see over here that insertion of the nitrene into tertiary carbon hydrogen bond is 67 times more as compared to the primary carbon hydrogen bond insertion. So this is how we can explain the selectivity, that tertiary is much more than the secondary than primary, and here secondary to primary was 9 is to 1. Here tertiary to primary is 67 is to 1. So these two examples very well explain the selectivity of insertion reactions in case of nitrenes. Then insertion reactions of nitrenes into carbon hydrogen bond may also lead to cyclization. If there is a possibility of cyclization, then we will get cyclic products in this case. So for example, if we are having this type of nitrene, this type of azide, when this is heated, this will eliminate one molecule of nitrogen gas, and a nitrene will be formed at this place, and this nitrene will insert at this carbon hydrogen bond. So this is carbon carbon double bond and one hydrogen attached at this place, then the nitrene formed at this place will add to that carbon hydrogen bond to get a cyclic product. So this is how, if there is a possibility of formation of a cyclic product, then such type of insertion will take place. and the formation of 5-membered rings is always much more stable than any other membered ring, that is 4-membered or 6-membered. If there is a possibility of formation of 5-membered, that will be the most stable transition state and they will always be preferred. Similarly over here, if we are having this type of nitrene and this carbon hydrogen bond can be inserted to give us a 5-membered cyclic structure through carbon hydrogen bond insertion through nitrenes. Then nitrenes, they undergo dimerization, and this reaction is used for the synthesis of azobenzene, and such type of compounds, they can be further used to form many type of dyes. So aryl nitrene undergo dimerization to give you azobenzene as the product. Then nitrenes, if there is a possibility of hydrogen abstraction, they can undergo hydrogen abstraction from the either from alpha carbon. When hydrogen abstraction is from alpha carbon, we will get Schiff's bases or amines as the product. Whereas if hydrogen is abstracted from 4 or 5 position, then we will get heterocyclic compounds as the product. If for example, if we are having this type of azide, that means with the elimination of one molecule of nitrogen gas, we will get a nitrene of this type. Here nitrogen will be having two lone pair of electrons, that means a nitrene intermediate will be formed when this is photochemically irradiated in presence of methyl alcohol. Now when this nitrene is formed, either hydrogen can be abstracted from this carbon. This carbon is the alpha carbon, right? And if hydrogen is abstracted from here, then this will create a carbon nitrogen double bond over here, and that hydrogen will be shifted to this nitrogen, and we will get this type of product which are called as amines, or we call it as Schiff's bases. Then this is position 1, 2, 3 and 4, and if hydrogen is abstracted from position 4, then this nitrogen will attack this carbon hydrogen bond and a cyclization will take place like this to give us 5-membered heterocyclic compounds. And similarly, if in any other compound there is a possibility of abstraction of hydrogen at 5 position, then we will get a 6-membered ring. So, but as I have told you that 5-membered ring formation is preferred over any other membered rings, that is 4-membered or 6-membered rings. Then is metal nitrene complex reactions, and among these reactions the most common one is the use of these reagents, iodinium imioids, and these are also known as amino iodines. Amino iodines, they are most commonly used in organic synthesis as precursors of nitrene, and these nitrene precursors, they can be used for addition reaction, that is addition of nitrenes to carbon carbon double bond to give us aziridiniums as the product, or it can undergo carbon hydrogen bond insertion in various types of organic substrates to give us amides as the product. So for example, if we are having this type of amino iodine, and with the elimination of phenyl iodide, this will give us a nitrene at this place, and this nitrene will add to this carbon carbon double bond to give us aziridines as the product. And the addition in this case is a syn addition, that is either from this side, and preferably this is added from this side, because the complex will form uh, a transition state with the oxygen present on the carbonyl and acetyl group. Similarly, in the second example, you can see that these amino iodines, they are generated from triplet cuprates in the presence of acetonitrile at room temperature, and these nitranes generated, they will add to this carbon-carbon double bond to give us stereospecific uh, addition of nitranes to carbon-carbon double bond, and the product formed is a stereospecific product. Then the addition to cis and trans stilbene, if we take here, the product formed is same in both the cases. The trans-aziridine product is formed, which suggests that in this case the mechanism is not a concerted mechanism but a two-step reaction mechanism. So either we react with cis-stilbene with this amino iodine, or we react with trans-stilbene with this amino iodine, the product formed in both the cases is same. That is, trans product is formed because this is thermodynamically more stable as compared to cis product. So that is why this product is formed. And formation of this single product from both the substrates tells us that there is a two-step reaction mechanism which is taking place. And we know that energy difference between triplet and singlet nitranes is very small, and interconversion at room temperature is possible when we are reacting these in presence of gold metal or copper acetyl acetonate. So any of these reaction conditions, what they will do is they will react with amino uh, iodines, and they will form a metal nitrene complex to generate the nitrene. And these nitranes will add in two-step reaction mechanism to give us these types of trans aziridines as the product. Then another is carbon hydrogen insertion reactions. The examples which we have seen now till this slide, they were all addition to carbon carbon double bond. Now we will see some examples of carbon hydrogen insertion through metal nitrene complexes. And again, amino iodines, they can catalyze these types of carbon hydrogen insertion reactions also in presence of some chiral manganese complexes. Chiral saline manganese 3 complex, when this is added at minus 40 degrees centigrade in presence of 1122 tetrachloroethane as the solvent, in 24 hours the insertion takes place at this position, carbon hydrogen bond, and we will get these types of amines as the product. So amidation at the saturated carbon hydrogen double bonds will take place. And most commonly used metal catalysts, they are ruthenium or manganese complexes, which are used for carbon hydrogen bond insertion reactions. And most commonly used substrate in these types of reactions, they are adamantane, this is adamantane, cyclohexene, ethyl benzene, cumene, indane, this is indane, tetraene, diphenylmethane. So all these they are hydrocarbons. So this is carbon-carbon double bond, whereas all others they are saturated alkenes. So these metal catalyzed ruthenium or magnesium complexes in presence of these types of reagents, they convert these hydrocarbons into these types of amines. So this carbon hydrogen bond is affected to give us these types of amino products in presence of iodine and dichloromethane as the solvent. So amino iodines in presence of iodine and dichloromethane will give us these types of adamantane derivatives. Then another example where palladium acetate is used, that 2-phenylpyridine, when this is reacted with palladium acetate, this will form a complex of this type. That two molecules of 2-phenylpyridine, they will react to form a complex with palladium acetate, and to this complex the nitrene will be inserted in these positions where the carbon palladium bond is there. So first what has happened, this hydrogen bond has been replaced by palladium carbon palladium in the transition state with the elimination of uh, acetate from palladium acetate and hydrogen from here. So then the nitrene will add to this position and this position of this molecule, and we will get methyl 2 pyridine 2-ol phenyl carbamates. So these types of carbamates, they are formed as the product, and reaction is carbon hydrogen insertion reaction. The nitrenes, they can also undergo ring expansion reactions. For example, if we are having this azide, we know when this will be irradiated with UV light in argon as the medium, then this will give us the nitrene with the elimination of one molecule of nitrogen gas, and then this nitrene formed can undergo this type of ring expansion, that this carbon nitrogen bond breaks from here and the 6-membered ring will become a 7-membered ring, and one lone pair of electrons will form a carbon nitrogen double bond like this. So one, this is the carbon nitrogen double bond, this has been formed, and one was already there. So these are uh, two carbon nitrogen double bond adjacent to each other, and these two structures, they are in equilibrium with each other. So this is how a ring expansion can take place in nitrenes. Then another route is that if this bond breaks, right, and this forms a carbon nitrogen double bond, this will break one electron from here, one electron from here, they will form a triple bond. One pair of electron will be shifted to create double bond, then one electron from here and one electron from here, this will create a carbon nitrogen triple bond, and we will get these types of diradical uh, intermediates. And then these two electrons, they can form a nitrogen nitrogen bond, and then ring contraction can take place like this. The 6-membered ring is converted into a 5-membered heterocyclic ring. So in the same reaction, either there is a possibility of ring expansion or there is a possibility of ring contraction, and this ring contraction can be achieved directly also if we heat this at 500 to 700 degree centigrade in FPT. So through diradical intermediate at a high temperature, we can get ring contracted products, or under these conditions we can have a ring expansion product. Then rearrangement reactions in case of nitrenes. Uh, as I have told you that there are many rearrangement reactions where nitrenes they are the intermediates, and these reactions are degradation of carboxylic acid derivatives to amines. So in all these rearrangement reactions, the product formed is same, that is amines, which is formed through nitrenes as the intermediate, but the starting material is different, but in all cases this is derived from carboxylic acids. So for example, in general, if we are having these types of substrates where this Z is bromo or chloro in case of Hoffman rearrangement, and if this Z is N2, that means total is N3, that is azide. If Z plus this nitrogen is azides, then this will be called as Curtius rearrangement. And if this Z is an ester, that is again a derivative of carboxylic acid, then this will be called as Lawson's rearrangement. So all these three rearrangements, if in the first step this Z group is eliminated, and we will get acyl nitrene as the intermediate. Then this acyl nitrene will rearrange to give us acyl isocyanates, alkyl isocyanates, and these alkyl isocyanates, they on hydrolysis will give us carbamic acids, which will ultimately degrade to give us amines as the product. So in all these reactions, the product will be amines, and these are called as rearrangement reactions. And these are the most common examples of uh, reactions where nitrene is an intermediate. Then another rearrangement of similar type is Schmidt rearrangement. So this is just a variation of the Curtius rearrangement. So here azides, they are formed from the reaction of carboxylic acid when this is heated with hydroxylic acid in the presence of an acid catalyst. So when carboxylic acid and hydroxylic acid, they are reacted in presence of acid catalyst, they will ultimately produce acyl azides, and these acyl azides, they are converted into amines through Curtius rearrangement. And in all these four rearrangements, as I have told you, that an intermediate which is there in the all rearrangements is a nitrene, and that nitrene in all the cases is converted into an alkyl isocyanate, and that isocyanate on hydrolysis gives us amines as the product. But the details of these rearrangement we will discuss later on one by one, and that what are the mechanisms of these, and what are the application of these rearrangements. But here, as far as in this lecture is concerned, the only thing we need to remember is that all these four rearrangements, they have nitrenes as the intermediate in their mechanism for conversion from different starting materials to amines as the products through isocyanates as another intermediates. Thank you very much. These are the different references which have been used. Advanced Organic Chemistry by Bruckner has been used for this lecture. Then Organic Reaction Mechanism by Singh and Mukherjee, Organic Reaction Mechanism Zeri March, and this review on iodinium imides has been used for metal nitrene complex reactions. In addition, some internet sources have also been used. Thank you very much.